Okay, students, Assalamu alaikum. Let's start with our today's lecture. So, just giving you a recap of what we have been doing so far and what we are continuing at this stage right now. This is the course of fluid mechanics. And so, in the very first lecture, you were first introduced what is a fluid. Okay, so we just discussed about what is a fluid. Then in lecture number 2 and 3, we discuss about the general fluid properties because you'll be dealing with fluid, so you should know what are the fluid properties. Okay, and we have been then using those fluid properties throughout in our analysis. So once we defined fluid in the first lecture and understood the fluid properties in the lecture number 2 and lecture number 3, then we move towards the very first thing in fluid mechanics, which is the fluid statics. As I told you, it is very similar to solid mechanics. You first study statics, then you study dynamics. So we studied in lecture number 4 and lecture number 5 fluid statics with the similar principles as you had the principles for the solid statics, but this is for the case of fluid instead of solid. Okay. So after studying solid statics, now we are going to start with, after studying fluid statics, now we are going to start with fluid dynamics. Within fluid mechanics, we are going to start with fluid dynamics. Now, if you remember, you studied solid dynamics, which by the name of the course dynamics you have studied. And in solid dynamics, what you used to do, you first used to study kinematics, then you used to study kinetics. So if I recall, you studied with using the textbook of Hibbler. Okay, so chapter number 12 was kinematics, and then 13, 14, 15 was kinetics, where you studied using the work principle, energy principle, because I've been teaching that course as well before, so I know this. So in the same way here in fluid mechanics, when we are going to study fluid dynamics, first we are going to study fluid kinematics. So today in this lecture, we are going to be introducing you to fluid kinematics, which is basically the beginning of dynamics. But once you go through kinematics, then we move towards fluid kinetics eventually. Okay. So overall principles and structures remain always the same. Yes, because the fluid is changed, because the material is changed. Previously, you were dealing with solids, now you're dealing with fluid. Obviously, there's going to be a lot difference in the analysis as well. But the basic structure of the analysis remains the same. Okay. So in this chapter, this is actually chapter number 4 of your textbook that we are studying right now. So we're going to start with the fluid flows and the pressure variation, okay, within the fluid flows. So first we are going to study fluid kinematics. So for fluid kinematics, what was kinematics? Kinematics was study of the motion. If you remember in dynamics, you had kinetics and kinematics. First you study kinetics. First you study kinematics. In kinematics, what did you study? You study the motion itself. Velocity, acceleration, things like that, different classification, tangential motion, normal motion, okay? So we studied the motion itself without taking into consideration that what were the factors behind that motion. In the same way, we are going to study here in fluid kinematics that we are going to first study the fluid motion itself without taking into consideration that what is the factor that is causing that motion. Obviously, when there is a motion, there is some reason behind that motion. Something is making it to move. But now, right now, when we are studying fluid kinematics, we are not going to focus over what is the reason behind that motion. We are not going to look into that. They're just going to focus over the motion itself. The motion parameters, motion classifications, what are the different kind of motions in the fluid we have. These are the things that we are going to study in fluid kinematics without looking into consideration that what was the cause of the motion. When we study the cause of the motion, that is fluid kinetics. And we are going to eventually go on to it, but not in this chapter, in the next chapter, so far. Okay. So we are going to discuss today description of the fluid motion, describing fluid flow patterns, laminar, turbulent flows, flow classification, acceleration, as I told you, fluid motion, that is velocity, acceleration, Euler's equation, Bernoulli's equation. Bernoulli's equation is a very common fundamental equation you might have. If you don't know it, at least you might have heard of it in fluid mechanics. Bernoulli's equation along a streamline and its application of Bernoulli's equation. We're going to talk about the rotational motion of a flowing fluid, pressure distribution in fluid rotating flows, Bernoulli's equation in irrotational flows, and then the separation phenomena. Okay, so these are actually it is it is a kind of a mixture of conceptual and numerical coursework material. Okay, so it's neither completely numerical nor completely conceptual, but it's a mixture. Okay, so we're going to be dealing with things accordingly. There are a lot of explanation and descriptions there within this lecture slides. Not all of it is important from the exam point of view. Yeah, all of it is important from the descriptive point of view, so for understanding the material. But for the exam point of view, whatever the things important, I will definitely going to be highlighting it during the lecture. Okay. So anybody have anything to ask so far? Okay. Let's move. Description of fluid motion. In order to calculate the forces exerted by moving fluids and to calculate the other effects of flow, such as transport, we must be able to describe the dynamics of flow mathematically. We are talking about that we are starting with the fluid dynamics. Okay. To discuss dynamics, we have to be able to describe the motion itself. Before studying that what is causing the motion, first we have to study the motion itself. Okay, and the description of motion is called kinematics. Okay, so we are interested in the kinematics of continuous media. This is a continuous media, as the continuum theory, as the continuum concept is applicable, that we studied in the very first chapter, in the very first lecture. Since you're already preparing for your quiz and you're already preparing for your midterm, so I'm sure you have gone through it already. And I'm very optimistic. Specifically, we are interested in describing the displacement, velocity, and acceleration of material points, very similar to you have studied in dynamics course. Velocity, displacement, acceleration. We're going to do that here again. To better understand and visualize the flow, we make use of imaginary lines such as streamlines, path lines, streak lines. So there are certain lines which we define, introduce to actually visualize the flow. So we're going to discuss about that. That's again related to the motion of the fluid. Okay, streamline is defined as a line drawn through the, we're going to study the streamline. Don't need to discuss it right now. Okay, so streamline is defined as the line drawn through a flow field in such a manner that the local velocity vector is tangent to the streamline at any point along the line at that instant. Okay, first of all, there is an engineering definition of something written here, but at the same time, you need to understand what does that thing physically means. Streamline is as simple as you can just hear it. Okay, how is the streamline? Well, how is the flow? You know that a fluid is flowing from one point to another point, and I can ask you, okay, tell me how is the flow? You're going to tell me that, okay, the fluid was starting from this point. Fluid was starting from this point. It continued like this, then it followed like this curve, then it went through this and like this, and then here it ended. Okay, there was no line in actuality. You draw it with your head. Just looking at the flow, you just see that how the flow is going, and you describe the flow motion, and that's the streamline. So first of all, it is an imaginary line. In reality, there is the flow, but there is no line. You draw the line in your own head just to show, to describe the flow, just to describe the stream. There is a flow, means stream. There is a stream going through, and you want to describe the stream by using a line, and that line is the streamline. So it's an imaginary line drawn just to show how the flow is going. So a streamline is defined as a line drawn through the flow field. Obviously, there is a flow field, a field where the flow is going is the flow field. In such a manner that the local velocity vector is tangent to the streamline. Local velocity vector is tangent to the streamline, means if you have a flow field and you pick a point on the flow field, the velocity is tangent to the streamline, means it is following the streamline. If you have any line, suppose this is a line, suppose this is a line, okay? So any point velocity will be, at any point the velocity will be tangent to that line, okay? Just to show that, okay, what is the direction of velocity at that point on the line, okay? Not this is whenever the fluid is flowing, whether it is following from somewhere, falling from somewhere, or maybe going upward, or maybe going on a horizontal path, okay? You can draw a line just to show how the fluid is flowing, and the velocity on that line is always tangent. So so let's say it's a horizontal flow, okay, and I draw a line, imaginary line, just to show, okay, the flow is going like this, okay. At any point on the line, if I want to figure out, if I want to point out what is the velocity at that point, the velocity direction at that point, the velocity direction at that point will always be tangent to that line. So if it is making a curve like this, at this point the velocity will be like this, at this point velocity will be like this, at this point velocity will be like this. Always tangent to my line. Similar to centrifugal process, but yes, in the centrifugal line process, it is also tangent to the curve. But I won't directly relate it to the centrifugal process. Centrifugal process is basically, centrifugal is a reaction to centripetal. So it's basically a centripetal process. Centripetal process is always involved whenever you have a curvature. Whenever you have a curvature, there is a centripetal process going on. So streamline in generally is just an imaginary line just to show that the flow is flowing from one point to another point, okay, and to just describe that how the fluid is flowing, okay. And obviously the streamlines will not converge with each other, will not meet with each other, because you're just making the imaginary lines to show the flow. Until and unless the flow itself, there are two separate flows which are coinciding with each other at some point, that's another case. But if you have a single fluid flow, then the streamlines will not be coinciding with each other. Okay? They'll just be following the path. Streamlines therefore show the flow direction. The main objective of the streamline is to show the flow direction. Okay. Streamlines are essentially a mathematical idea. It is very useful in many fluid flow analysis, but there is no way to make a streamline directly visible. In reality, there is no streamline in reality. Okay, so we just make it hypothetically in our mind just to show the flow direction, flow motion. So velocity is a function of distance and time. Okay. So suppose if you have a tank like this and there is fluid flowing out of the tank, so you'll draw the streamlines like this. Now the streamlines in reality are not there, but they are drawn here like this just to show that the velocity, that the fluid is actually moving out of the tank like this. So we have drawn the streamline just to show how the fluid flows. Okay, suppose if I have an aerofoil and the fluid is flowing across the aerofoil. So how would the fluid flow? I am just making the streamlines to show that what would be the direction of the flow as it passes. You mean here? This one? Yes. It will be on the line. How do you draw a tangent on a straight line? On the line. On a curve, it will be on one single point, but if it is a straight line, it will be on the line. It's clear? Okay, so this is just to show that how the streamlines are drawn. Okay. Stagnation point. Stagnation point is basically what point? Actually, most of the time, the English terminologies are used, and they are exact definition of how. No, stagnant means we use it in English. This is very stagnant, means it is not changing. It is constant. It is not changing. It is fixed. Okay. So sometimes when the fluid encounters an object in a way that it has to stop at one point, the fluid is actually stopping at that point, then that point is known as the stagnation point. Okay. You see here the streamlines above, they are just adjusting themselves so that they avoid the object. But there are some of the streamline that they cannot avoid the object, so they actually strike the object and actually stops at that point. So that point where the fluid stream actually stops because of the intersection with the object, because of the what do you say, because of the coincidence with the object. Okay, so that point is known as stagnation point. For the stagnation point, velocity is 0. This is important here. For a stagnation point, velocity will be 0. Okay. When I say this is an important point, it means I don't know how, but I might use it somehow in the exam to judge whether you understand what does a stagnation point mean or not. Okay. So stagnation point is a point where the velocity within the flow stream becomes equals to 0 at that point. Okay, so that was the streamline. Now we have another line to define the flow. We call it path line. Now, path line is a trajectory or path of a given fluid element or a line drawn through a flow field in such a way that it defines the path that a given particle of the fluid has taken. Suppose if a fluid is flowing through some point, okay, what I do is that I take a small piece of tissue paper and put it in the fluid. So now the tissue paper is going to flow as the fluid will be flowing, and I can actually see the tissue paper. The path followed by that tissue paper would be the path line. Now this is a real thing. Streamline was not real thing. It was in our imaginary, but in our head we draw some lines. But path lines are the real things. Okay, so you attach something to a particle, fluid particle, which is flowing. And now as the fluid particle will flow, that thing will flow, and the path which is covered by that particle is actually the path followed by the fluid particle. Okay, so path lines are the real lines. They can intersect. आप दो टिश्यू पेपर के पीसेस डाल दें, हो सकता है वो दोनों टिश्यू पेपर के पीसेस आपस में टकरा भी जाएं कहीं पर. But the streamlines will not intersect because they are not the real lines. We are just making them to show the path. Yeah. If the fluid is smooth, if the fluid is following the way we want it to flow, then it will not. There won't be any intersections. So path line is a real line. It is a trajectory or a path of a given fluid element or a line drawn through a flow field in such a way that it defines the path that a given particle of fluid has taken. It provides us a history of particles location. Where was the particle before? Obviously, you need a camera, and then you need to draw it later on to see how the fluid particle flowed. Okay, this is something happens when you sometimes you go to hospital and they give you a pill to swallow, and within the pill there is a camera and it follows the path, and you can actually see the particle where it is going through and whatever it is experiencing. Okay. This is just one example. There could be multiple examples. Okay. Okay. Then we have another line which is known as a streak line. Now, what is a streak line? Streak line is also another line which is used to define a fluid flow, and this is something used very commonly. Suppose there is a fluid flowing through, there is a fluid flow field. fluid is flowing. Okay, now if I look at it, it looks like, because there are no lines visible. I can see the fluid, but there are no lines visible. Okay, and if there is no specific turbulence, then sometimes it becomes almost impossible to judge where the fluid is flowing. Okay, so what you do is that you take a pen, ink pen, okay, and put the pen in the fluid. Now, pen is not one place, but as the fluid will be flowing through the pen, it is going to take the ink with it, and the ink line will be formed. Okay. Now, the ink line is formed. Why? Because all the fluid particles which passes through that point where the pen was there, okay, they took the ink particles with it, and then you can see that how the fluid is flowing. Okay, now you are not tracking a single particle. Path line was when you were tracking a single particle. Now you are not tracking a single particle. Now you are tracking all the particles which has passed through a single point. Suppose you want to see that, okay, how the air is moving here. I know there is air. I know there is motion of air. I cannot see it. Okay, I light a cigarette. I put a cigarette in my hand. There is smoke coming from the cigarette. I can see now where the smoke is going. The line drawn by the smoke will be the streak line. I am not following a particle, but I am looking at the line which has passed through the point from where the smoke is coming. Okay, so this is known as, obviously. Okay, so let's say if there is a little flow of air in the room, okay, and I put a cigarette, so you can exactly see the smoke line. Now the smoke line is formed not because I am following a specific particle, it's because all the particles which has passed through the cigarette are now taking the smoke with it, so a line is formed. So this is not a path line. Path line is for a single particle. This is multiple particles passing through a single point. So this is, we call it streak line. So these are different, these are the different lines which are used to describe the path. Sometimes we need path line, sometimes we need streak lines, sometimes we are just using our imagination to describe the flow by using the streamlines. Okay. Normally, if we have a steady flow, smooth flow, then the path line, streak line, streamline, all will be same. But in case if we have a very smooth flow, steady flow, ideal flow. So this point is important here, which I'm highlighting. When the flow is, oh no, not this one, this one. In a steady flow, each particle coming across the same fixed point moves down the same path, and therefore the streak line is identical to the path line and the streamline. All the three lines are same when the flow is steady and smooth. Okay. But there are different ways of describing the flow. These are some of the animations. If you go and watch these animations on the YouTube, you're going to find these animations which are showing the path line, streamline, streak lines, okay, within the fluid flow. So we are studying the flow right now without giving into consideration that what are the factors behind the flow. Just the flow itself we are studying. Right now we are discussing the flow classification. There are different flow classifications. Okay, how to define the flow? Okay. So one most commonly used flow classification is if the flow is laminar or turbulent. Most significant, most widely used, okay, classification if the flow is laminar or turbulent. Okay, do you have any idea what is the difference between laminar and turbulent flow? Ever heard it before? Any idea? I want to hear from you. What is a laminar flow? What is a turbulent flow? Okay. And turbulent. Disturbed. Okay, good. Anybody else? It's okay. It's okay. This you're right. Okay, good. Again, as I told you, we are using English as a medium, so basic English terminologies are used. Turbulence. या बहुत ज़्यादा उर्दू में क्या बोलेंगे हिजानी कैफियत so turbulence. Okay, so this is turbulence. Opposite of it is laminar. Laminar means linear, means smooth, calm, steady, right? Like this. So this is how it is. If I generally define, laminar flow is a very smooth flow. Turbulent flow is haphazard. There's a lot of disturbance. A flow which is disturbed. When you look at the flow, you looks like that, okay, the flow is hugely disturbed. Okay. But if it is laminar flow, it's very calm, steady, smooth. In generally, laminar flows are the flows which are of comparatively less velocity. Turbulent flows are the flows which are comparatively of higher velocity. But this definition is not correct. We cannot define just by velocity whether the flow is laminar or turbulent. Okay, there is a specific criteria through which we can actually determine if the flow is smooth or the flow is disturbed. So smooth is laminar, disturbed is turbulent. Okay. So laminar flow is a flow in which the fluid flow with no significant mixing or ongoing fluid or of neighboring fluid particles. The flow may be steady or unsteady. Okay, turbulent flows in which the fluid flow motion vary irregularly. Okay, so that the quantities such as velocity, pressure show random variation with time and space coordinates. These are the technical definitions. But in reality, physically, if you want to say laminar means smooth flow, turbulent means disturbed flow. This is the definition. Multiple factors. Okay. We are going to discuss those factors later on. Okay, not right now. Right now, our focus is just to classify different kind of flows. We have a lot of flows in the world. I want to classify them. Okay, put them in classes. This is this class of fluid. This is another class of fluid flow. This is a third class of fluid flow. So right now, our objective is that. So you can see here, this is a figurative way of showing this is laminar flow, very smooth. And here you see the turbulence is now very visible at this point. Okay. See, there is a smoke coming out of something. You can see the smoke is initially laminar, then now this is turbulent. So whenever you have a laminar flow, the flow is smooth, can be defined with a velocity profile specific. Okay, but for the turbulent flow, there is some disturbance which is there over the regular flow. So you have a mean flow, and then over the mean flow there is disturbance. So that is a turbulent flow. How do we define it? It's there is a terminology. There is a number, we call it dimensionless number, which is the Reynolds number. Now, Reynolds number is the basic number through which we can actually define whether the flow is smooth or the flow is disturbed. Okay, the formula for the Reynolds number is this. Density into velocity multiplied by length divided by viscosity. So if the density is high, then the Reynolds number can become high. If the velocity is high, the fluid is moving fast, then the Reynolds number can become high. If the fluid has been flowing for a very long time, characteristic length to which the fluid has flown, then the Reynolds number can become high. But the viscosity, if the viscosity is low, then the Reynolds number will be high. So it's not just a single factor. There are 4 factors involved. Okay. Yeah, we can say that those ones for which the velocity is high, their Reynolds number is high, so probably they will be the turbulent flow, but not necessary. Even there are flows for which the velocity is very high, but still they are laminar flow. Why? Because maybe the other factors are such that the overall Reynolds number is less. Okay, sometimes there are flows which are very slow in motion, but in reality they are turbulent flows. For example, if you have seen lava flowing, lava flows very slowly, but it is a highly turbulent flow. Okay, there's a lot of disturbance in it. Okay, velocity is less, but not necessarily that it is a laminar flow just because of velocity. Because it's not just the velocity, there are other factors as well. What is the density? वो fluid कितना भारी है? What is the viscosity? वो fluid कितना गाढ़ा या पतला है? How long the fluid has been moving from the start point? Okay, so the fluid which has been moving for a very long time from the start point automatically become turbulent. Okay? The turbulence is induced in it. It becomes disturbed flow. Okay? So there are multiple factors. Okay, so basic thing is that we have a critical Reynolds number through which we define mathematically whether a flow is laminar or turbulent. And that critical Reynolds number for an open flows are 5 into 10 to the power 5. If the critical Reynolds number is less than 5 into 10 to the power 5, then we consider it as laminar. Otherwise, if it is greater than that, this value, then we consider it as turbulent. Okay, this is for the open flows. For the closed flows, where you have, for example, a pipe or a duct which is closed and the fluid is moving through them, the critical Reynolds number is 2000. So less than 2000, we will consider it laminar. If it is greater than 2000, we will consider it turbulent. Okay, but anyways, these are again there is a lot of description about it, and we are going to discuss it later on in the course. These are just some of the preliminary values to show you or to describe the basic concept of laminar and turbulent flows discussed here. Okay. So what are the things we have discussed? Right now we want to discuss the flow. So we discussed that how the flow is described by using streamline, streak line, path line. Then we classified the flow into two categories: smooth flow and disturbed flow, which is a laminar flow and turbulent flow. Now there are further few more classifications of the fluid flow. Okay, the first type of classification is uniform flow and non-uniform flow. Okay, when we say uniform flow or non-uniform flow, uniformity is a function of distance. Uniformity is a function of distance or space, because distance could be in x direction, could be in y direction, could be in z direction. So it generally means space. So suppose a fluid is moving in space, such that the velocity of the fluid is changing. So at this point, the velocity of fluid is v1. At this point, the velocity of fluid is v2. And what I am saying is that v1 is not equal to v2. If suppose this is the case, that the fluid, either the velocity is increasing or decreasing while it is moving in space. So the position of v1 is position, let's say x1, position of v2 is x2. So they are not the same place. They are not the same point. They are different points in space. So if the fluid is moving in space such that its velocity is changing from point to point within space, then we call it a non-uniform flow. But if its velocity is not changing, so that means if I'm saying that at x1 velocity is v1 and x2 velocity is v2, but v1 is equal to v2, both are same, that means it is a uniform flow. So when the fluid is moving in space such that the velocity is not changing from point to point in space, then it is a uniform flow. But if the velocity is changing from point to point in space, then it is a non-uniform flow. So there is a specific meaning of uniform or non-uniform flow in fluid mechanics. Do you understand it or not? So mathematically, how are you going to say there is a velocity variation with space, dava v by dava s. Why we are using dava? Because we already know that the velocity has other factors through which it can vary as well. But right now we are just considering one of the factors. So I'm using instead of capital instead of d, I'm using dava. So dava v by dava s, velocity variation with space is equals to 0 if it is uniform flow. For non-uniform flow, velocity variation with space will not be equal to 0. There will be variation means. Okay. Now there are different ways. For example, a converging flow. You have a nozzle and the fluid is moving through the nozzle. So what will happen in nozzle? It's a pipe with a decreasing diameter. We have studied in thermodynamics. It's a pipe with a decreasing diameter. So what will happen as the fluid flows through the nozzle, it has to pass through the same small opening of the pipe. So its speed is going to increase. Okay. So the velocity is changing from the beginning of the nozzle to the end of the nozzle. Okay, when we say that the velocity is changing, we means the velocity is changing. But velocity is composed of two things, magnitude and direction. So if the magnitude is changing, that means the velocity is changing. But suppose the magnitude is not changing, but direction is changing, still velocity is changing. So suppose I have a circular flow. This is a vortex. Vortex is a circular flow. And suppose at any point in the vortex, if you check the velocity here, V1, you check the velocity here, V2, you check the velocity here, V3, maybe V1 equals to V2 equals to V3. All the velocities are same in magnitude. But still, it is a non-uniform flow. Why? Because magnitude is same, but the direction is changing. It's a circular path. So if the direction is changing, then the velocity is also changing. Magnitude might be same, but the velocity direction is changing. That also changes the velocity. Because the velocity is a vector quantity, it's composed of two things, not just the magnitude, direction is also there. So do you understand the flow classification? Uniform, non-uniform flow. It deals with the space, variation of velocity in space. Now let's move over to another classification, steady and unsteady flow. These have specific meanings. When we say steady flow, it means the velocity is not changing with time. So what does this mean? Suppose the fluid is moving like this. Okay. So at this point, velocity is V1. At this point, velocity is V2. Now I'm saying that V1 is not equal to V2. So that is a non-uniform flow. But when I'm looking at the steady flow or unsteady flow, so I have to not look along the path. I have to look at a single point at different time. So initially, what is the velocity V1 at time t equals to 0? And what is the velocity V1 at time equals to 2 seconds, let's say. If V1 at time 0 and V1 at time at 2 seconds are both same, then we say that the flow is steady. But if V1 at time 0 is not the same as V1 at time 2, that means it is unsteady. So I'm not looking in space. I'm looking at a specific point, but with the time. Okay. So if I change the time, will the velocity be changing or not? So at different time, if the velocity is not changing, then it is a steady flow. But if the velocity is changing with time, then it is unsteady flow. Okay. The most common example is that you go in your house or you open the water tap. You keep it like this. Now the water is coming from the water tap at a constant speed. You're not changing the speed right now. You check the speed now, check the speed after 5 minutes, check the speed after 10 minutes. Same. If the velocity is not changing with time, then it is steady. Now, a flow can be steady and uniform. A flow can be steady and non-uniform. A flow can be unsteady and uniform. A flow can be unsteady and non-uniform because they are two different dimensions. Changing in space and changing with time are two different things. Maybe a fluid flow is changing its velocity in space as well as with time. Maybe it is not changing in space but changing with time. Maybe it is, you can make the combinations. I get messed up in my mind. Okay. Abhi aayegi example. So for the case of steady and unsteady flow, how do we define it? With dava V by dava T with time. It was that for the uniform, non-uniform, it was dava V by dava S with space. Okay. So far, no numerical has came, all conceptual concepts. Okay. So this chapter, there are a lot of conceptual concepts, and I can ask any of those conceptual concepts. What is the difference between streamline, straight line, path line? Where do we use these? Okay. And what is the difference between laminar and turbulent flow? What causes laminar flow to become turbulent flow? If you increase the density, if you increase the velocity, if you decrease the viscosity, okay, the formula is there. Based on that, okay, what is the critical Reynolds number? Okay, what is the difference between uniform, non-uniform flow? What is the difference between steady and unsteady flow? So many questions that can be asked conceptually. 1 mark, 2 mark. I can ask 5, 6 questions. The examples here. The flow through a long uniform diameter pipe at a constant rate is a steady uniform flow. So आपके पास एक पाइप है, उससे फ्लो जा रहा है और फ्लो की रफ्तार चेंज नहीं कर रहा है आप, जहां से भी फ्लो निकल रहा है. लेट्स से वो पाइप आप कह लें आपके किचन का सिंक का नल है, ठीक है. तो आपने अगर टैप को एक बार घुमा के छोड़ दिया, पानी आ रहा है उससे, ठीक है ना. वो पाइप भी कांस्टेंट डायमीटर पाइप है, पाइप का डायमीटर चेंज नहीं हो रहा. सो देन इट इज बेसिकली यूनिफॉर्म फ्लो. क्योंकि डायमीटर चेंज होगा तो रफ्तार बढ़ेगी, डायमीटर कम होगा तो रफ्तार बढ़ जाएगी. इफ द डायमीटर इंक्रीज होगा तो रफ्तार कम हो जाएगी, ठीक है. लेकिन अगर डायमीटर चेंज नहीं हो रहा तो रफ्तार तो सेम रहेगी पानी की, until and unless you do not change the tap. Okay, so it's a uniform flow and it is a steady flow. With time also change नहीं हो रहा क्योंकि आपने time आप change नहीं कर रहे tap. Okay, second example, a flow through a long uniform diameter pipe at varying rate. पाइप तो यूनिफॉर्म था लेकिन आप टैप चेंज कर रहे हैं विद टाइम. आप यू आर इंक्रीजिंग द फ्लो, यू आर डिक्रीजिंग द फ्लो विद टाइम, ठीक है. तो अगर उस नल के ऊपर आप किसी भी पॉइंट पर वेलोसिटी लेंगे तो सारे पॉइंट्स पर वेलोसिटी सेम होगी. लेकिन अगर आप पोजीशन टैप की चेंज करेंगे तो सबकी एक साथ वेलोसिटी चेंज हो रही होगी. सो इट इज अ अनस्टेडी फ्लो बिकॉज यू आर चेंजिंग द टैप. But uniform flow, क्योंकि at any point the diameter is same, so the velocity is same. A steady or unsteady ये हाँ with time आप change कर रहे हैं. With time you are changing the flow. If you are changing the flow with time, that is unsteady. If you are not changing the flow with time, that is steady. Okay. Then flow through a long diverging pipe. Diverging pipe मतलब जो पाइप ओपन हो रहा हो ज्यादा आगे जाके. तो अगर आपका डायमीटर चेंज हो रहा है तो होगा ये कि डायमीटर अगर डिक्रीज होता है तो पाइप की वेलोसिटी, फ्लो की वेलोसिटी बढ़ जाती है. आपने देखा ना, नोजल जो होता है आपके पास, जो स्प्रे नोजल होता है वो, उसमें आगे बहुत ज्यादा स्मॉल ओपनिंग हो जाती है. स्मॉल ओपनिंग की वजह से रफ्तार बहुत तेज बढ़ जाती है, वो प्रेशर स्पीड के साथ आता है वाटर, ठीक है. तो लेकिन अगर आपके पास फ्लो ओपनिंग, इफ यू इंक्रीज द फ्लो ओपनिंग तो रफ्तार कम हो जाएगी. So if it is a diverging flow or a converging flow, in both ways it will be non-uniform. क्योंकि along the length आप देखेंगे तो velocities different होंगी. Starting पे velocity different होगी compared to the end point. But let's say you do not change the tap. Tap आपने same रखा हुआ है with time, so it's a steady. But if you are also changing the tap with time, then it becomes unsteady as well as non-uniform. Okay, so these are 4 examples of uniform flow and non-uniform flow, steady flow, unsteady flow. Okay. So these were some basic flow classifications that we have discussed. Then there is also another flow classification based upon the dimensionality. One-dimensional flow. One-dimensional flow is what? A flow which is varying in a single dimension. It's not flow is flowing, it's a three-dimensional fluid flow. But among the three dimensions, in two dimensions, it is fixed. It's not varying. But in one of the dimension, it is varying. Okay. So that is known as one-dimensional flow. For example, flow through a pipe. अब इसमें pipe में along the radius ही vary कर रहा है, क्योंकि at the edges the fluid will be stationary. So pipe is stationary है, no slip condition, it will be stationary. In the center line, fluid will be very fast. So along the radius ही fluid vary कर रहा है. And radius is one dimension in cylindrical coordinates. Okay. Let's say if your pipe is not circular, suppose it is a duct. Now it's square. तो अब तो रेडियस भी वेरी कर रहा है ना, अब तो एक रेडियस तो होगा नहीं, बिकॉज इट इज अ स्क्वायर. सर्कल का तो एक रेडियस होता है, स्क्वायर का तो एक रेडियस नहीं होता. सो नाउ इट विल बी वेरिंग इन एक्स एंड वाई डायरेक्शन. अभी भी इस डायरेक्शन में, जिस डायरेक्शन में फ्लो कर रहा है उसमें तो फिक्स ही होगा फ्लो, ठीक है ना, एक्स एंड वाई डायरेक्शन में फ्लो वेरी करेगा. सो नाउ इट्स अ टू डायमेंशनल फ्लो. सपोज कि वो पाइप इज कन्वर्जिंग या डाइवर्जिंग, तो अब ये थ्री डायमेंशनल फ्लो हो गया. एक्स वाई में भी वेरी कर रहा है और फिर जेड डायरेक्शन में भी वेरी कर रहा है, बिकॉज ऑफ पाइप डायमीटर इज इंक्रीजिंग और डिक्रीजिंग. गेट द आइडिया? So when we say one dimensional flow, two dimensional flow, three dimensional flow, it does not mean that the fluid is flowing only in one direction. It just means that the variation in the fluid flow is only in one direction. In the other direction, it is constant. So a lot of flow classifications that we have gone through. Okay. Steady flow, unsteady flow, uniform, non-uniform, laminar, turbulent, path line, streamline, streak lines, one dimensional, two dimensional, three dimensional. Next is the topic of acceleration. We have just discussed the motion. Velocity. अभी तो हम सारी velocity पर बात कर रहे थे. Velocity with space change हो रही है, with time change हो रही है. ठीक है. Velocity ज़्यादा है, कम है, laminar, turbulent है. So we were just discussing with the velocity. We are going through fluid kinematics right now. Now we are going to move towards the next topic, which is the acceleration. Okay. So do you want a break before that right now, or should I continue? Okay. Chalo. Okay, no problem. Okay, so acceleration. Acceleration is change in velocity with time. Simple. Okay. When I'm teaching, nothing is simple. So acceleration is change in velocity with time. I've gone through it many times, many times. Okay. But the velocity is a vector quantity. Now the complications start. It's a vector quantity. It has a magnitude. It has a direction. So when we say change in velocity, what does it mean? Will change in the magnitude? It might be change in magnitude only. It might be change in direction only. It might be change in both magnitude and direction. And when we are talking about magnitude, then we have discussed it that they could be uniform, non-uniform, they could be steady, unsteady. The magnitude could be changing with space, could be changing with time. Further branches emerge. Okay, so you see here, dv by dt is basically, now velocity can be written as a component of magnitude and direction. So this is the magnitude and this is direction, ut, tangential. This is direction. Okay. And but for V, I have to write here in bracket S and T, because V, velocity magnitude, is a function of space and time. It could be changing with the space, could be changing with time. Okay. Now let's talk about the magnitude first. Okay. You know, if you have two terms and you are differentiating with respect to something, then what do we call it? Chain rule. You keep one term constant, take the differential with the other, then keep the other constant, take the differential with the first. So now there are two terms, magnitude and velocity. Sorry, magnitude and direction, right? So first keep one term constant, ut, right? There are two terms, ut and v. First take ut constant and take the differential with time of the magnitude. Okay, so it should be dv by dt. But we know that v is a function of s and t. So instead of using v d, I'm going to use dava, because there are two factors, right? So I will rather say that it should be dava v by dava t, right? Plus dava v by dava t. What I can do is that I can multiply this thing by dava s by dava s. It's not going to change anything. Okay, but how then I can write here dava s by dava t is velocity v, right? So it could be written as dava v by dava t plus velocity into dava v by dava s. Do you understand what I did? d by dt, dv by dt split कर दिया दो पार्ट में, dava v by dava t, dava v by dava t. But I have to include dava v by dava s. So what I do is that for one of the part I multiply by dava s by dava s. Dava s by dava s is 1. You multiply anything by 1, it does not change anything. But now I can rearrange it, because dava s by dava t is the velocity. Dava s by dava t is the velocity, and dava v by dava s now has come in the equation. So dava dv by dt can be written as dv by dava v by dava t plus v dava v by dava s. ऐड क्यों कर रहे हैं? बिकॉज एक चीज है वो वेरी कर रही है दो चीज से, तो आप उसको कहें कि स्प्लिट कर दिया, dv by dt, dv by dt को मैंने दो हिस्सों में स्प्लिट कर दिया, दोनों ही dv डावा v by डावा t थे, बट एक के साथ मैंने डावा s by डावा s मल्टीप्लाई किया, because I need to introduce dava v by dava s, because velocity variation with s is also there. Now this is a small, मैंने डिस्क्रिप्शन करके आपको शो किया है, बट इन रियलिटी ये शो नहीं हुआ होता कहीं पे भी. व्हाई? बिकॉज you have already taken the math courses and considered that you are already excellent in it. Okay, so this is not needed. But anyways, आपको शो कर दिया है. Okay. Although I know that you don't need this explanation. So d by dt v ut, so ut को पहले कॉमन लिया और फिर dv by dt को स्प्लिट कर दिया. Okay, so now we have, this is the first term of the chain rule. Now the second term will be, now I'm not going to explain this in any way, this is centripetal acceleration. Now what we are saying is that change in the velocity with time, sorry, change in the direction with time. Change in the direction with time gives the or provides the concept of centripetal acceleration. Now centripetal acceleration is not new to you. You have been studying it from class 9. V square upon r, right? So v square upon r is the magnitude of centripetal acceleration. I don't need to go into the derivation that how does v square upon r come. It is centripetal acceleration. You have been studying from class 9 onward. Okay, and obviously the direction of it is the normal direction. Centripetal acceleration की direction किधर होती है? Towards the center. Tangential की तो होती है, हाँ, not centrifugal. Tangential की direction होती है along the tangent, but centripetal की direction होती है along the center. I take a string, attach a stone to it, and I make it around. Okay, I revolve it. Okay, जो centripetal acceleration होगी वो तो towards me होगी, which is holding the stone in that orbit. मैंने ये लगाया हुआ है. Yes. Centripetal acceleration will only be applicable if you have a curvature. Have a logical look at it. If there is no curvature, what will be the radius? It will become infinity. So infinity is there in the denominator. It will become 0. So if there is no curvature, it's a straight path, centripetal factor goes out. This is actually one of the short questions. Okay. So do you understand here this? अभी लास्ट यही तो बोला मैंने. Look, if देखें, अगर हमारे पास ये है, इसका कर्वेचर है, तो कर्वेचर you can see that what is the radius. ठीक है. अगर मैं कर्वेचर इसका बढ़ाता जाऊं तो रेडियस बढ़ता जाएगा. If I make it a straight path, तो रेडियस infinite हो जाएगा. So if the radius will become infinite, then r is there in the denominator. It would become 0. So for a straight line, why does the centripetal factor goes 0? Because the radius goes infinity. This is a short question.
How? So we would be starting from those that are
ये तो जनरल फॉर्मेट हो गया ना, जिसके अंदर कर्वेचर भी इंक्लूडेड है, वेरिएशन ऑफ वेलोसिटी विद टाइम भी है, वेरिएशन वेलोसिटी विद स्पेस भी है. बट इफ नाउ यू हैव डिफरेंट कंडीशंस, suppose the flow is not suppose the motion is not varying with time, so which term will cancel? This term will cancel. If the motion is not varying with space, which term will cancel? This term will cancel. If the motion is in a straight path, no curvature, then which term will cancel? This term will cancel, right? So what we have done is that we have derived a general equation, general format of the equation. Okay. The first term of the above equation is the tangential component of acceleration. This is the tangential component of acceleration. The second term is the normal component of acceleration. This is the normal component of acceleration, also called centripetal acceleration. Okay. Pura tangential component, whether variation with space or variation with time. But this is only the variation in magnitude. And so it is the tangential component. Now the thing is that velocity is also a three-dimensional quantity. So you can have a velocity component in x direction, you can have a velocity component in y direction, you can have a velocity component in z direction. Okay, now चीज और complicate होती चली जाएगी. First you introduce normal component and tangential component, then you say okay, within tangential component there is a variation with space and variation with time. And you further introduce that space is also x, y, z. So equation को फैलाते चले जा रहे हैं. Okay. Nothing is easy when I'm teaching. Okay. Okay. So v could be written as a function of x, y, and z with x and y, z, x, y, and z coordinates. The x component of the velocity is written as u, y component of the velocity is written as v, z component of the velocity is written as w. U, v, and w are the x, y, z component of the velocities, which itself are components of x, y, z, and time. So u is a function of x, y, z, and time. V is a function of x, y, z, and time. Or further और फैला लें इसको. Z is a function of x, y, z, and time. Okay. So acceleration के भी different components होंगे, x, y, z components. So ax, ay, az. Okay. So now we define something as total derivative. Total derivative. Total derivative means total change. Because total change could be the change with the time, change with the space in X direction, in Y direction, in Z direction, could be the change in the direction. It's the normal component. We include everything together, that becomes the total derivative. Okay, so that's why it is written with capital D. You have been using small d and DAVA, but this thing is written as capital D. So capital D, what is the difference between small d and capital D? When you are writing small d, you are discussing change with one thing. But when you are writing capital D, then you are including all the possible factors that could be there for the change of this component. Okay, for the change of this specific variable. Okay, so AX is equals to du by dt, change in the X component of velocity with time, but total change. So total change will involve what? It will involve, now you see here, this is basically the vector format written. So you can expand it because you know velocity is a function of X, Y, Z, UV and W components. So you can expand this, and the expansion will come up with this term. So it will be U du by dx plus V du by dy plus omega du by dz. Okay, plus du by dt. Okay, so du by dt. Okay, whenever you have a variation with time, we call it local. Now this is again a terminology used. Local variation. Local means variation with time. Whenever we have variation with the space, the terminology used in fluid mechanics is convective. So convective acceleration and local acceleration component. Local acceleration component deals with the steady and unsteady. Convective acceleration component deals with the uniform, non-uniform. Right? So convective acceleration term is this: U du by dx, V dv by dy, V du by dy, omega du by dz. And local acceleration will be du by dt. This is the X component of acceleration. Similarly, you can have Y component of acceleration. The only difference is that instead of U, now you have V. Then you can have Z component of acceleration. Instead of U, now you have omega W. But you'll have the local components and you can have the convective components. And this is all tangential. Centripetal is something different. V square upon R. Right? These are all tangential. Okay. So the total derivative term will be this: d by dt, capital D by dt equals to U d by dx plus V d by dy. We call this as operator, total derivative operator. Okay. I couldn't understand what you want to say. Yeah, if you integrate it, you're going to get the velocity. After you have got the acceleration, if you integrate it, you're going to get the velocity. So local acceleration, what is local acceleration? The terms involving derivative with respect to time. The remaining terms with respect to space is the convective acceleration. In steady flow, local acceleration is 0. In uniform flow, convective acceleration is 0. Uniform flow, there is no change with the space. So convective term will become 0. Okay. So now I can give you the entire equation. I can ask you that, okay, simplify this equation for steady flow. So then which term you have to cancel? Variation with time, because there's steady flow, no variation with time. I can ask you that simplify this equation for uniform flow. Then which term you have to cancel? All the terms with dava by dava x, dava by dava y, dava by dava z, those you have to cancel. Because no variation in flow if it is uniform flow. I can say that, okay, it is a flow in a straight line. And which term you have to cancel? The Centripetal acceleration term you have to cancel. We have to show that r goes infinity because it is a straight line, so that's why this term goes 0. Okay. A lot of explanation. Okay. Have a break of 10 minutes, okay? It is 4:20 right now. By 4:30 we're going to start, okay?
So if we were to calculate the acceleration of a fluid to the flow whether can the simultaneously we have curvature as well as non-curvature. So both of those acceleration can calculate.
Most of the time what we do is then we split the problem into multiple parts. The part where there is curvature, we solve it separately. The part where there is no curvature, we solve it separately.
But it cannot be a universal problem.
No, no, universal. Okay, so let's start with the numerical. Evaluating acceleration in a nozzle. So we have a nozzle, and in the nozzle, the fluid is flowing through the nozzle. So nozzle is basically a pipe with a reducing diameter. So at the beginning, you have a big diameter. Comparatively, in the end, you have a smaller diameter. So a nozzle is designed such that the velocity in the nozzle varies as follows. So this is the variation of velocity in the nozzle. It's provided in the question. This variation is only in the u direction, means in the x direction. And this is equals to u naught over 1 minus 0.5 x by L, where the velocity u naught is the entrance velocity and L is the nozzle length. The entrance velocity is 10 meter per second. So value of u naught is given. And the length is 0.5 meter. So length is also given. The velocity is uniform across each section. So at any section, the velocity is uniform. Okay. Uniform means at any section, whether velocity I see here or velocity here or velocity here, at any section it is uniform. It's not changing. Okay. The velocity is uniform across each section. Find the acceleration at the station halfway through the nozzle. So now it's a function of x. So we need to find the velocity at point halfway through the nozzle, means x by L equals to 0.5. For a value of x by L equals to 0.5, I want to know that what is the velocity at that point. What is the acceleration at that point? Okay. So before moving over to the problem solution, first of all, do you understand the problem statement? So you have a nozzle, fluid is flowing through the nozzle. Within the nozzle, how the velocity distribution is there, it is provided. Okay, and you need to find that at the center of the nozzle, what is the acceleration of this fluid? Is there anything within the problem statement or the problem diagram which is not clear to you? So you can ask. So let's move over to the solution. Okay, so we are talking about acceleration and the velocity is given. So that means we have to use the total derivative. Okay, so there were total derivative terminologies. If you look here, these were the total derivative. Okay, first of all, velocity is given only as a function of x. So it's and in the u direction. So we don't have v direction velocity. So the acceleration will be ax only. Okay, so we have ax. This is the term. Okay, so u is a function of x only. So there is no du by dy, there is no du by dz, and u is also not a function of time. It was just a function of x. So this term will also be 0. So what we are left up with, we want to find acceleration. So it will be only ax, which will be equals to u du by dx. Okay, so this is what we need to do. This is a question. We have u as a function of x. We need to first find u du by dx. That will be ax. Okay. Then for the normal component, because the velocity is in a straight line. Okay. So there will not be any normal component as well. Okay, so the only component of velocity will be acceleration will be there will be the x component, and that will be the total acceleration. Okay, so this is what we have to do. So first we find out what is dou u by dou x, since u was given as a function of x. So dou u by dou x will be this thing. Now how it comes this thing, I don't have to explain this, it's simple. Here x is there in the denominator, and you are differentiating it with x. So how you do it? I don't have to explain this. This is simple derivation. Yes. Yes. So it becomes, you see, this becomes power 2. And then after that, you differentiate the original term without the power. So you got this thing. Okay. Then you multiply this by u, because we need to find u du by dx. So once you have du by dx, multiply by u, so you get this term. Again, in this term, u naught is known, L is known, x by L is also known. Why? Because we have to do it for x by L 0.5. In the question it is given, do it for x by L 0.5. Okay. So if you just substitute all the values, you're going to get u du by dx equals to 237 meter per second square. So that's the value. It should be u, not add, multiply. Yeah, so we have to multiply this term. The whole this term multiply by this term. So you see here, there was a square, now it is cube. Okay. So local acceleration term 0, centripetal acceleration term 0. So the only acceleration term that we will have will be ax, which will be 237 meter per second square, no normal term, and that's the solution to this problem. Is the problem and its solution clear or not? Okay, now let's come over to another topic, which is the Euler's equation. Recall that in chapter number 3, the pressure variation in a static fluid was considered. So we developed the equation for hydrostatic pressure variation within the fluid. Okay, so Euler's equation concerns pressure variation in an acceleration fluid. So what's the difference? First, if we did it for a case, suppose I have a glass or jug of water, the water is stationary in it. So we did it for hydrostatic variation of pressure in water. So how the pressure will vary from the top to the bottom to the further bottom, if you vary the elevation, how the pressure is going to vary. First, we did it that in chapter number 3. Now this is the case. It is the same glass or jug of water filled with water. I'm not moving the water. I'm moving the jug. I'm moving the container which is containing the water. So the water is in motion because the jug is in motion. But water itself is not in motion. It is still static. But what do we say? It's a partial static because it is in motion because of the container, motion of the container. So for example, you have, you might have seen water tankers. The tanker is moving and mashallah, they move at a very high speed. Okay. So even in a very rush environment, you have to save yourself. Okay. They are not going to take care. So they move at a very high speed. The water itself is not in motion, but the tanker is in motion. So here Euler's equation is applied. Okay. So Euler's equation is applied for the case of the fluids where the fluid itself is not in motion, but the container in which it is contained, that container is in motion. Okay, so Euler equation concerns pressure variation. It also discusses the pressure variation in an accelerating fluid. The fluid is accelerating. in which there is no velocity gradient within the fluid. Because fluid itself is not moving, so the layers of fluids are all stationary. So there is no velocity gradient between the layers of the fluid. But the fluid is accelerating because the container is moving. Okay. Therefore, viscous effects will not be considered. So viscous effects will not be there. Remember, viscous effects will always be there when the fluid itself is in motion. When the fluid itself is in motion, then the layers of fluid might be moving at a relatively different speed. So whenever there are two layers of fluid which are in contact with each other but moving at a relatively different speed with each other, so there's going to be friction between the layers of the fluid, and that friction causes viscous effects. Okay. So, but if all the fluid layers are moving at the same speed, then there is no relative motion, so viscous effects are not there. Okay. So thus the viscous forces will not be considered in the analysis. An example of such case is a tank of liquid carried by a truck. Derivation of Euler's equation is similar to the derivation of the hydrostatic differential equation. It is derived by summation F is equals to ma for a fluid particle. Now, if you remember, when we derived it for the case of hydrostatic pressure variation in a fluid, we said summation F equals to 0. We said summation F equals to 0. Now we are not saying summation F equals to 0. Now we are saying summation F is equals to MAT, because there is now acceleration because of the tank which is moving. Okay, so that's the only difference. Okay, otherwise the derivation remains exactly the same. You have the cylindrical fluid element like we had before. You had the pressure component on one end, or pressure component on the other end. Pressure component of on one end was P del A. Pressure component on the other end was P plus del P del A. Okay, pressure always acts inward. Okay, so one is considered as positive, the other component is considered as negative. Okay, there is mass. Mass can be written as density into volume. Volume is del A into del L. Okay, there is weight. Weight can be written as gamma into volume. So volume is again del A into del L. Okay, same analysis. We considered a tilt of this at angle alpha. Okay, like we did it in the case of the hydrostatic pressure variation, variation of pressure in fluids. Okay, so so we have the weight component, we have the pressure component. Okay, weight plus pressure component equals to ma at. Okay, substitute the values. Okay, this is for the case of the pressure component, this will be for the case of the weight component. We have sine alpha because I told you that we are going to consider this angle. Okay, so this alpha will be the same as alpha here, and correspondingly we can make a right angle triangle and say sine alpha is equals to del z by del L, like we did in the hydrostatic variation of pressure derivation. Okay, then substituting all the values, dividing by del A, del L, taking the limits such as del L approaches 0, we get this equation. Okay, we get this equation. So it's dava P by dava L negative gamma dava Z by dava L equals to rho AL. Or we can write it as, if we take this common, dava by dava L common, so it becomes negative dava by dava L P plus gamma Z equals to rho AL. Okay, or negative del PZ equals to rho A. This is the derivation. In previous case, when the tank was itself stationary, it was not moving, there was no acceleration AL. Okay, you see here, this AL acceleration was not there. So the only difference will be that this term will not be there. And we will return back to the hydrostatic equation. This is the hydrostatic equation. Simple. Okay, hydrostatic equation, if you remember, it says negative dava by dava L P plus gamma Z equals to 0 means P plus gamma Z equals to constant. And we said that piezometric pressure is constant. P plus gamma Z was piezometric pressure, was constant. Now the only factor is that now we have an additional acceleration, which is AL. This is also there now. Since this is also there, so this is the Euler's equation. So Euler's equation and hydrostatic equation for the pressure variation are exactly the same. Only the difference is that in the case of the Euler's equation, the tank itself is in motion. So we are not saying summation F equals to 0. We are saying summation F is equals to MA. That's the only difference. Okay. So if you understand the hydrostatic equation of pressure variation and Euler's equation is, there is no difference in it. It's exactly the same. derivation wise. Okay. So now we have got this term, gradient of piezometric pressure field. This thing is equals to rho A. Okay, rho is mass over volume and area, and A is the acceleration of the particle. Okay. Note that when there is no acceleration, the Euler's equation reduces to hydrostatic pressure variation in a fluid, where P plus gamma Z equals to constant. In other words, along a direction in which there is no acceleration, the pressure distribution is hydrostatic. For example, pressure variation normal to the streamline is hydrostatic. This term, this paragraph is important for the short questions point of view. Conceptual wise question: what is the relationship between Euler's equation and a hydrostatic pressure variation in a fluid? This paragraph answers this question. And so if I want to ask this question in the exam, relate the Euler's equation with the hydrostatic equation of pressure variation, your answer will come from this paragraph. Okay. So many conceptual things. When a fluid particle is changing speed, then the pressure will vary in the direction that is tangent to the streamline. Okay, this is a concept. When the streamlines are straight and parallel, then piezometric pressure will be constant along a line normal to the streamlines. So when you have constant streamlines, the normal to those streamline will have the same piezometric pressure. Again, it's an understandable concept. For the curved, when the streamlines are curved, then piezometric pressure increases outward and from the center of curvature of the streamlines. This is all from the formulation. Okay. So now let's move towards a numerical, solve a problem. A water column or column of water in a vertical tube is being accelerated by a piston in the vertical direction at 100 meters per second square. The depth of the water column is 10 centimeters. Find the gauge pressure on the piston. The water density is 1000 kg per meter cube. So you have this situation that you have a water column here. This is the water column. Okay. In this water column, you have a piston here. Above the piston, there is water. So what is happening is that this piston is moving up. This piston is moving up. So when this piston is moving up, we need to find out okay, how much with what speed it is moving up. This at 100 meters per second square. This acceleration is moving up. The depth of the water column is 10 centimeters. So this is 10 centimeter, the water column depth. Okay, and find the gauge pressure on the piston. So we want to know what is the pressure on the piston at this point. What is the pressure on the piston at this point? Okay, when the piston is moving up. Pressure आएगा because of the acceleration. And it's very simple. You know, you can see अगर आप एक एलिवेटर पर खड़े हुए हैं और एलिवेटर ऊपर जा रही है, जितनी रफ्तार से एलिवेटर जाएगी आप नीचे को धंसेंगे. So basically the effect of the acceleration in the opposite direction will be there. एलिवेटर ऊपर जा रही है पर आपका प्रेशर नीचे पड़ेगा. ठीक है, उसी हिसाब में just think about it कि एलिवेटर अगर नीचे बहुत तेज रफ्तारी से जाती है तो आपको लगेगा जैसे आप ऊपर उठ रहे हैं. Okay. So this is simply explained by this Euler's formula. Okay, before moving towards the problem solution, always it is important to ask, do you understand the problem statement and the diagram? Okay, if you understand the problem statement and diagram, then we'll move forward towards the solution. Okay, so now let's move towards the solution, because this is a case where the water is in itself is not flowing. This is not a flowing fluid, but the container which is containing the water, that container is moving. Okay, so this is a case where Euler's equation will be applied. So always keep that in mind. If the water is stationary and the container is stationary, then hydrostatic equation of pressure variation will be applied. But if the container is in motion, but the water is not flowing, but the container is in motion, then the Euler's equation will be applied. Okay. So we know what is the Euler's equation. Euler's equation, if needed, will be provided to you in the exam. Okay, so Euler's equation, if needed, will be provided to you in the exam. So this is the Euler's equation. d by dz p plus gamma z equals to negative rho az. Okay. Now what I have to do is that I have to integrate this from 1 to 2. From 1 to 2, I can integrate it. If I integrate it from 1 to 2, I can put this dz on the other side. Okay. So it becomes dp plus gamma z equals to negative rho az dz integrated from 1 to 2. So it will become p2 plus gamma z2 minus p1 plus gamma z1. This will be the simple integral of this thing. Okay. And here it will be what? It will be, because rho az are constant. The acceleration is constant and density is also constant. So they both the terms are going to come out of the integral. Okay. So it will be just dz. So it will be negative rho az z2 minus z1. Right? We'll have this thing. Achha, in this case, this is considered as open to atmosphere. Top side is considered open to atmosphere. Open to atmosphere means gauge pressure will be 0. Okay. So P2 will be 0. Okay. So now if you rearrange, put P1 on one side, all the other terms on the other side. So you're going to get this thing. Okay. So gamma plus rho az into del z. Okay. So again, you know that gamma is rho g. So take rho also common. So it becomes rho g plus az into del z. Okay. You know the density. It's given in the question. G is 9.81. Acceleration 100. And del z here, it's 10 centimeter. So that's the depth. Just substitute the values. You're going to get the pressure here. Get the pressure here. If the container was closed from the top, then at least we need to know what is the pressure inside the container. At one point, you need the pressure. Depends. Okay. Yeah, then P2 won't be 0. Okay, then you have to know what is P2. You need one starting point to reach to the other point. But if one is not even a single starting point is given, then you cannot reach any solution. Okay. So there's always suppose ये container in motion नहीं होता, तो फिर हमारे पास hydrostatic equation of pressure variation would be applied. In that case, इस फॉर्मूले में क्या चेंज आता? सिर्फ ये चेंज आता कि AZ हमारे पास नहीं होता, बाकी सब वही सेम रहता. अगर मैं AZ को हटा दूं इधर से, तो ये मेरे पास हाइड्रोस्टैटिक इक्वेशन ऑफ प्रेशर वेरिएशन बन जाती है. As simple as that, right? So now consider this thing. Let's say exam में यही question I give this in the exam, but एक part इसमें add कर देता हूँ. Suppose if the piston is not moving, then what will be the pressure on the piston? तो उस केस में आपके पास फॉर्मुलेशन यही यूज होगी, बस AZ put it 0, right? But this you know if you have gone through the lecture, and you don't know if you have not gone through the next lecture. You won't find this question in the book. Okay, so whatever I'm teaching, paper उसी से आएगा और बस. But during the teaching, I also tell that what are the modifications I can put for the exam. Those modifications at that time when I'm teaching it, they are pretty understandable, and students can easily, if they are following through, they can easily know that what would be the solution for this modification. The thing is that in the exam, if you have not followed through the lecture and then this modification come, then you will be surprised that, okay, I don't know what to do. So, but fortunately the lectures are being recorded. So in case if somebody wants to view them, they can view them in the future. But there will be modification. Okay. Sometimes I change the values, but the numerical values that I change most of the times are so, you can say, they are thought, after a thought process I change them, because those changing in the values make a significant change in the solution procedure. Okay, so they are not just random. And sometimes like for example, in this question, I told you that I will, let's say if I provide the same question, but with an added part. that, okay, also find it out for the case if the piston is not moving. Okay, then you're going to return back to hydrostatic equation of pressure variation.
This lecture is not included in the
It's not included in the midterm, but it might be included in quiz 2, it might be included in final. So there are a lot of things. Okay, so now let's discuss this problem. Pressure in a decelerating tank of liquid. A tank on the trailer truck is filled completely with gasoline. So what is gasoline? Gasoline is not a gas. Petrol. But the other name for petrol is gasoline. Okay. The tank on the trailer truck is filled completely with gasoline, which has a specific weight of 42 pound-feet per feet cube. The truck is decelerating at a rate of 10 feet per second square. If the tank on the trailer is 20 feet long and if the pressure at the top rear end of the tank is atmospheric, what is the pressure at the top front end? What is the rear end and the front end? So, yeah, rear पीछे को कहते हैं, front आगे को कहते हैं. So for a truck, front end would be the front of the tank, rear end would be the back of the tank. Okay. If the tank is 6 feet high, what is the maximum pressure in the tank? Okay, so the first thing is, that we need to understand the problem statement. हमारे पास, we have this tank. The tank was moving at a very high speed. I don't know what was the speed. It's not mentioned, but it is decelerating. और किसी ने ब्रेक मारा है tank पे. अब जब tank पे ब्रेक मारेंगे तो फिर tank की रफ्तार slow होगी. It will start slowing down. Okay. जो deceleration है इसकी, वो है 10 feet per second square और 3.05 meter per second square. Deceleration. Okay. अच्छा. You have to understand one thing कि whenever there is acceleration or deceleration, जो hydrostatic or you can say जो हमारे पास streamlines है, they vary. आपको simple example इसकी I can give. आप एक glass of water लें जिसको half fill करें, उसको तेजी से यूं move करें, so you will find कि जो glass का water level है जो पहले यूं था, जब आप तेजी से यूं move करेंगे तो वो water level during the motion यूं हो जाएगा, right? तेजी से ग्लास को यूं मूव किया तो जो वाटर लेवल यूं था ड्यूरिंग द मोशन वो लेवल यूं हो जाएगा. जैसी ग्लास स्टेशनरी होगा वापस वो सीधा हो जाएगा. अगर आप इसको यूं मूव करेंगे तो वो ग्लास का लेवल इट विल बिकम लाइक दिस एंड देन व्हेन यू स्टॉप इट विल बिकम रिटर्न. करके देखना कभी. टेक अ ग्लास ऑफ वाटर, हाफ फिल इट. वो बात और है कि जब आप तेजी से मूव करेंगे बाद में पानी गिर जाएगा पूरा, लेकिन एक्सपेरिमेंट हो जाएगा. ठीक है. Okay, so if you do like this, quickly move करेंगे तो जो water का level है वो it would vary. So these water levels which was initially like horizontal, then if suppose you are moving like this, it will become like this. If you are moving like this, then the water level will become like this. Okay. So now in this case, these water levels, okay, these water lines, they are the constant pressure lines. So constant pressure lines were horizontal when it is stationary. But if it is in motion, the constant pressure line vary. Okay. So the constant pressure line tilt according to the motion. Now, just imagine it. The tank was in motion and suddenly a person put the brake. अब वो ब्रेक डाल रहा है तो टैंक बहुत तेजी से स्लो होगा. Because of the slowing effect of the tank, acceleration हमारे पास यूं हो जाएगी, right? और जो constant pressure line है वो हमारे पास किस तरीके से होगी, वो हमारे पास यूं हो जाएगी constant pressure line. Instead of horizontal, constant pressure line will tilt in the opposite direction जब आपको ब्रेक डालना है. अगर ब्रेक नहीं डालते, एक्सेलरेटर डालते, तो constant pressure line कैसे होती, फिर यूं हो जाती, right? Just imagine the truck is moving, the constant pressure line पीछे को चली जाएगी. ठीक है. तो जब ब्रेक मारा तो उसके अपोजिट होगा, right? So the thing is that previously, suppose if the tank was not in motion, then at the top level, let's say the tank is filled with gasoline, completely filled with gasoline, then at the top level, we would have the same pressure from the front end to the rear end. We would have the same pressure because it's a horizontal line. But when the tank is moving, now it won't be the same pressure from the front to the rear end at the top level. Why? Because the constant pressure lines have been tilted. Okay. So it is said that if the tank on the trailer is 20 feet and if the pressure at the top rear end of the tank is atmospheric, here it is atmospheric pressure. So gauge pressure will be 0 at the top rear end. This is not the front end. This is the rear end, backside. So at the top rear end, the pressure is atmospheric. So what is the pressure at the top front end? So we want to know, okay, at this point, what is the pressure? This is part A. And the second thing is that what is the highest pressure, maximum pressure in the tank? Obviously, the pressure variation within the tank will always be, if the pressure increases as the elevation goes down. Okay, so at the bottom of the tank, you will have the highest pressure, but at the bottom of the tank, at the front end, you will have the highest pressure. Since you will have at the front end, you will have comparatively the highest pressure, okay, because the tank is decelerating. So part B will be to find out the pressure at the bottom front end, because that would be the point where you'll have the highest pressure when the tank is decelerating. अगर टैंक एक्सेलरेट कर रहा हो तो फिर बॉटम रियर एंड पर हमारे पास हाईएस्ट प्रेशर होगा. जब हमारे पास इस मोशन में एक्सेलरेशन हो रही है तो जाहिर सी बात है सारा प्रेशर बैक साइड पे शिफ्ट हो जाएगा और बैक साइड पे भी सबसे बॉटम पे सबसे ज्यादा प्रेशर होगा. So this is the problem statement. Before moving towards the solution, first of all, do you understand the problem statement? Once again with this statement. Tank on the trailer truck is filled completely with gasoline, which has a specific weight of 6.6 kilonewton per meter cube. The truck is decelerating at a rate of 10 feet per second square. If the tank on the trailer is 20 feet long and if the pressure at the top rear end of the tank is atmospheric, अगर इस point पर pressure atmospheric है, okay, what is the pressure at the top front end? So first of all, here we will have Euler's equation applied because the tank is in motion. Okay. Suppose if the tank was not in motion, then it would be the hydrostatic pressure variation, and in that case, top front end पे भी pressure 0 ही होता, क्योंकि वो horizontal line पर और non-horizontal line pressure remains constant. In case of hydrostatic pressure variation, when the fluid body is not in motion, okay, but when the fluid body is in motion, तो फिर हमारे पास जो constant pressure lines हैं वो horizontal नहीं रहती. That remains tilted, that become tilted. The tilt is in the direction where the acceleration is. Okay. तो अगर acceleration यूं होगी तो tilt ऐसा हो जाएगा, अगर acceleration यूं होगी तो tilting हो जाएगा. Okay, but that depends. This also depends on how much is the acceleration. That depends upon the tilt. जितनी ज़्यादा acceleration होगी उतना ज़्यादा tilt होगा, जितनी कम acceleration होगी उतना कम tilt होगा. Okay. So now we have to find out, first of all, if the pressure here at the back to a top rear end is atmospheric, what will be the pressure at the top front end? This is one thing. Then the second thing is that what will be the maximum pressure in the tank under this condition? The maximum pressure will always be at the bottom. It will not be at the top. It will always be at the bottom. Okay. Or because the tank is decelerating, so it will be bottom front end. If it was decelerating, if it was accelerating, then it would be bottom rear end. Okay. अच्छा, we have not yet started solving the example. लेकिन अब मैं modification क्या कर सकता हूँ exam में? Let's say I give you the same problem, but what I say is that instead of decelerating, I'm saying it is accelerating. Okay. So if I'm saying it is accelerating, so what will happen? Problem will change in the sense कि हमारे पास पे जो maximum pressure वो top front end की जगह वो bottom front end पे आ जाएगा, right? I can also add a part into it that suppose when the truck is stationary, okay, then what is the maximum pressure? And then what is the maximum pressure? Will it be at front end or at the rear end? What will be the answer then? Front end or rear end पे same होगा pressure. If the tank is not in motion. Okay. How will you justify that Euler's equation should be applied here? Because the fluid itself is not in motion, but the container containing the fluid, that container is in motion. So the Euler's equation is applicable. So you can have a numerical with the theoretical questions associated with it in the exam as well. Okay. Okay, if the problem statement and the diagram is clear, then I move towards the solution. If anybody have any question within the problem statement or the diagram, then you can ask. Let's move towards the solution. So since Euler's equation is applicable, so we are going to use the Euler's equation. This is the Euler's equation. dP by dL equals to negative rho AL. Okay, this is the Euler's equation. So if we integrate it, so it will become P2 minus P1, which is equals to negative rho AL del L, right? Which will be equal to negative gamma by G. Rho can be written as gamma by G. Okay, because gamma is equals to rho G. Okay, so rho can be written as gamma by G, AL into del L. Okay. Now we can just substitute the values. Gamma is given. Okay, G is known. Then acceleration is given, was negative 10. Okay, and we know that how much is the length. Okay, we know what is the how long was the was the container. Okay, so because we are moving, we know this pressure, so we are moving from the rear end. We are moving from the rear end to the front end. Okay. So if you substitute the values, you're going to get what is P2. P1 will be 0 because P1 is the atmospheric pressure, which is mentioned as the gauge pressure to be 0. Okay. So this is also done in the SI units. So you get to what is P2. The next thing is that now we need to find out in the vertical direction, because we need to find out what is the maximum. The acceleration was in the x direction. There was no acceleration in the vertical direction. So it will be again, if we apply the Euler's equation for the vertical direction, AZ will be 0. Horizontal direction, we call it AL, it was not 0 because the tank was decelerating in the horizontal direction. But in the vertical direction, it is 0. Tank is not moving up and down. It is moving in the x direction, you can say, or the L direction. Okay. So again, we apply the Euler's equation, but with AZ equals to 0. If you put AZ equals to 0, it becomes the hydrostatic equation. Okay, so it becomes simple hydrostatic equation. What does hydrostatic equation say? Piezometric pressure is constant. P plus gamma Z is a constant. So that means P2 plus gamma Z2 will be equal to P3 plus gamma Z3. If we say that this is 0.1, if we say this is 0.1, this is 0.2, and this is 0.3, right? So we, between 2 and 3, we can apply hydrostatic equation of pressure variation. Okay? Because there is no acceleration in the Z direction, in up and down. Okay, so it's just P2 plus gamma Z2 equals to P3 plus gamma Z3. Okay, so we already know what is P2. We have just calculated what is P2. So correspondingly, we know what is P2. Okay, Z2 and Z3 are known because we know what is Z2 minus Z3. We know what is the height. Okay, gamma is known. So just substitute the values. You're going to get what is P3. This is also done in the SI units. So you can find out what is the maximum pressure in the tank. Okay. Anybody have anything to ask? It's not really that difficult, but the Euler's derivation you missed. When we were discussing the Euler's derivation, where the Euler's application equation will be applied, you missed that. Okay, but it is there in the videos. When you watch it, then you will understand it easily. There's a problem with all the courses actually, but specifically in fluid mechanics, thermodynamics, and these thermal courses, things are developing over one another. You miss something in between, you will find yourself lost. Okay, but you can catch up easily if you have the videos. Okay? So the only thing you have to do is just watch the video, and go through with the lecture, so you will understand. I can answer if there is a specific question that this is the part that you don't understand. But generic, it's very difficult, I cannot answer. Yeah, it's in generally, fluid mechanics is not that easy. Depends how depth you are going in. So normally when I teach, it is not easy because I go in a lot of depth. So, but this is the requirement as per the policy of the course and the course specifications and the syllabus. Anyways, still, if you don't understand any topic, feel free to let me know. We will repeat that. Okay. But you have to help me out in the way that you have to go through the material first that you have missed by going through the videos and going through the lecture yourself first. Otherwise, it's just teaching it twice and thrice the same material. Okay. So because we have a huge course and we have a limited amount of time. So normally I intend not to waste time. Okay. So even if one student is there in the class, I just start the lecture, keeping that in mind that the lecture is being recorded and those who are missing the material can catch up later on. Okay. But I cannot wait for everybody to come and then I start. In that case, I'm going to lose a lot of time. Okay. Okay, there is one thing here that, as I told you, whenever there is the container is in motion, there is acceleration. Because of that, the constant pressure lines will not remain horizontal. It will tilt according to the motion based on the direction of acceleration. If the acceleration is in the positive x direction, then the tilt will be like this. If the acceleration is like this, the tilt will be like this. If the acceleration is like this, tilt would be like this. But depends upon what will be the angle of this tilt, depend upon the actual magnitude of the acceleration. Okay, and there is a specific formulation through which we can find out that what would be the specific angle of this tilt. Okay, and there is a small derivation. I'm not going through this derivation. You can go through it yourself. The end result is this: tan alpha. If I say alpha is the tilt, if I say alpha is the tilt, then tan alpha is equals to ax by g. Ax is the acceleration in the x direction, and g is the acceleration due to gravity. Okay, so how much will be this tilt? Depends upon this. If ax is higher, obviously, then tan alpha will be higher. Okay, so you can find out the angle alpha if you know what is the acceleration in the x direction. At the same time, you know what is g. So based on that, you can find out what will be this angle alpha. So again, this formula will be provided to you in the exam if needed. This formula will be provided to you in the exam if needed. And I can add a part in the last question. In the last question, that tank was in deceleration. And so I can add that, also find out the angle of tilt. Okay. So because you know G and you already find out the acceleration was actually given, not find out. It was given in the question. How much was the deceleration? Just put the value of acceleration, put the value of G, find out alpha. So I can just simply add a part in the last question along with providing you the formula. Okay. But it will be easy for those who have gone through the lecture to actually do it. Those who have not gone through the lecture or not seen the video, they might feel it at something new was given in the exam. Okay. So this is not new, no surprises if you have gone through. This is the general solution for Euler's equation in 2 dimensions. We did the Euler's equation in 1 dimension. This is the solution for the Euler's equation in 2 dimensions. I don't want to go through it. There is no, we are not covering the Euler's equation in 2 dimensions, but it is there in the lecture slides in case you are curious and you want to go through it and you are enthusiastic, and of course, you are more than welcome. Okay, so next topic is a very important topic, Bernoulli's equation. Bernoulli did a lot of work, and now you have to do a lot of work because Bernoulli did a lot of work and published it. Okay, so Bernoulli's equation is actually an extension from Euler's equation. But now we are actually considering the fluid motion. Previously in Euler's equation, we are saying that the fluid was stationary, but the container within the fluid in which the fluid was contained, that container was moving. Now in case of Bernoulli, we are saying that no, now the fluid is actually in motion. However, still we put some limitations. In engineering in general, whether you belong to any branch of engineering, we first start with the simplest thing, then we start adding complications to that. Make it a little more complicated. Then when we are comfortable with it, okay, make it a little more complicated. In the end, we want to approach to the realistic things, which are the most complicated things. The practical realistic things, which has all the variables, all the things included into it, they are the most complicated things, but you cannot directly start from there. If you start from there, you don't understand anything. So we start from the simplest thing and then we start adding complication. So first we started with fluid statics, hydrostatic pressure variation in a fluid. Fluid is not in motion, the container is not in motion. Then we added a little complication into it and say, okay, now we're still saying that the fluid is not in motion, but the container in which the fluid is, that container is in motion. So we come up with the Euler's equation. Now we are going to add some more complication into it. Now we say, okay, now actually the fluid is in motion. Previously the fluid was not in motion, just the container was in motion. But now I'm saying that, okay, the fluid is in motion, but still we are going to put some assumptions in it to simplify it. Okay, so we are moving towards a more complicated thing, but still making assumptions to make the problem simpler. Later on, we are going to remove those assumptions as well to approach the realistic topic, to approach the realistic fluid flow motion. Okay, so now let's have a look at it. That was the Euler's equation. That was the Euler's equation. Dava by dava s, negative dava by dava x, p plus gamma z equals to rho at. Okay, now what we are saying is that the fluid is moving in a streamline, on a streamline, whatever the streamline is. It could be a straight line, it could be a curve, whatever the curve it is. Okay, so this is a streamline and we say that it is defined as S. X direction is X, Y direction is Y, Z direction is Z, and S is any path. So it's path S. We call it a streamline. Okay, the fluid is moving through the streamline, and within the streamline, obviously the acceleration here is there is tangential acceleration. Okay, there is a fluid rho at. Okay, there is spray azan going on. Let's have a wait. Let's wait 2 to 3 minutes, then we will start. Okay, so what we say is that what will be this tangential acceleration? Tangential acceleration will be v dava v by dava s plus dava v by dava t. We already gone through it. We already gone through it, that how tangential acceleration is equal to this thing. Okay, now first of all we say that the flow is steady. So this is the first condition that we impose. The flow is steady. So we are saying that now the fluid is moving, but it is steady. Its motion is not changing with time. At any point, whatever the velocity, the velocity remains the same at that point with time. Whatever the time it is, it remains the same. So we are putting limitations to simplify our problem. Okay. So first of all, we say that it is steady. So when it is steady means what? It means this term cancels. So we end up into this thing. V by dava s. Okay. From the beginning, we are actually starting from the Euler's equation. And Euler's equation was for the inviscid flow. Inviscid flow is what? Where the viscous effects are negligible, are ignorable. And why viscous effects are ignorable? Viscous effects are ignorable because the fluid layers there is no relative motion between the fluid. All the layers are either stationary or moving with the same speed. If all the layers of the fluid are moving with the same speed, then there is no relative motion between the fluid elements. If there is no relative motion between the fluid layers, then the viscous effects are not there. There is no resistance between the layers of fluid. It is there, but it is not applicable. Okay? Application comes when there is relative motion between the layers of fluid. Okay. So we are already starting from the Euler's equation. So this condition is already there in viscid flow condition. So condition number 2 is already there. Again, we put a condition of steady flow. So dava v by dava t is cancelled. So these are the two limitations right now we have imposed. Okay. So now our equation becomes what? Negative dava by dava s. It will be previously it was a function of s and t. So I was writing dava. Now it's just a function of s. It's not a function of t. So instead of writing dava, I can write d. Right? So I will write here negative d by ds p plus gamma z equals to rho v dv by ds. Rho is coming from this formula here, and then at is v dv by ds. Right? So we get to this point. Till this point, it is clear or not? Till this point, it is clear or not? Negative d by ds p plus gamma z equals to rho v dv by ds. Okay. Now what we are going to say is that we are saying that look, this term here is v dv by ds. Okay. If I write here d by ds v square by 2. If I differentiate v square by 2 by with respect to s. So what will be the answer? It will be 2 it will be 2v upon 2 into dv upon ds, because it is differentiating with respect to s. Okay, 2 and 2 will cancel, right? So it is v dv by ds. So instead of writing v dv by ds, I can write this thing, d by ds v square upon 2, because they both are the same thing. So here we have v dv by ds. Instead of writing v dv by ds, what I do is that I write d by ds v square upon 2. Right? Now I am putting the third condition. The third condition is that the fluid is incompressible. Fluid is incompressible. So incompressible means the density is not varying. That means you cannot apply this for gases. Gases are compressible. Liquid are incompressible. So that means one of the conditions for Bernoulli is that it has to be sensitive applied only for incompressible. That means you can apply Bernoulli only for the case of liquids. If you apply Bernoulli for the gases, you can do it, but then I will do something else. Okay, so this is the. So now I put I put density inside the integral. I'll put density inside the integral. Okay, so it becomes d by ds v rho v square upon 2. Here I had negative d by ds p plus gamma z from the Euler's equation. Okay, I take this thing on the other side of the equation. So I can put everything inside differential. So that means p plus gamma z plus rho v square upon 2, this whole d by ds equals to 0. This is my Bernoulli's equation. Bernoulli's equation is P plus gamma Z plus rho V square upon 2 equals to 0. But in order to come up to Bernoulli equation, I have applied 4 limitations. First of all, the flow should be steady, should not be varying with time. It cannot be applied for gases. The flow should be incompressible. Then it should be along the streamline. Whatever the flow is moving along the streamline, it has to be along the streamline, okay? Because we are using d by ds. We integrate it, then it has to be along the streamline, okay? So S is the streamline, okay? And the fourth condition is that from the starting point, it should be inviscid flow. Inviscid flow means viscous effect should not be there, but we are saying that it is actually the fluid motion. So normally what happens is that suppose I have a container or suppose I have a pipe, okay, and the fluid is moving through the pipe, okay. So wherever I have the boundaries, pipe boundary, there I will have viscous effects there. Why? Because at the boundary, flow will be stationary, and then you have different layers of fluid with a different relative speeds. Okay, so there will be relative motion. So viscous effects will be there at the boundary. So at the boundary, you cannot apply Bernoulli's equation. Yeah, but in the central line, in the central region, the flow will be almost uniform. It will be all moving with the same speed. So viscous effects will not be there. So Bernoulli equation can only be applied in areas where the viscous effects are not there. So that means it cannot be applied where you have boundaries, where you have relative motion between the layers of the fluid. Okay. So, but if you have a bulk motion of fluid in the central region, almost all the fluid layers are moving with the same speed. So you can apply Bernoulli equation there. You can apply Bernoulli equation only if the flow is steady. There is no variation with time. You can apply Bernoulli equation only when the flow is incompressible. You cannot apply it on gases. Okay. And it has to be along the streamline. So these are the 4 conditions which we are now applying over to the fluid flow. But with these 4 conditions applied, we can apply the Bernoulli equation. Okay. So now we have made our, we are moving towards a comparatively more complicated thing. Euler's was that fluid itself is not in motion, but the container was in motion. Now we are saying the fluid itself is in motion, but we put certain limitations. Steady flow, incompressible flow along the streamline, and inviscid flow. So a short question. What are the limitations of Bernoulli's equation? 4 marks, 4 points. Incompressible flow, inviscid flow along the streamline, steady. I don't find these words. You can write the whole paragraph. I'm not going to give you a single mark, but I will be looking for these words. Okay. You write these words in a single line, you got full marks. Straight away to the point answer. No need for big stories. Okay. So what are the conditions of, what are the limitations for Bernoulli's equation where it is applied? Okay. Okay. So the Bernoulli's equation says that P plus gamma Z plus rho V square upon 2 equals to 0, differential of it along the streamline. That means P plus gamma Z plus rho V square upon 2 equals to constant. Now, what is its relationship with the hydrostatic equation of pressure variation? In hydrostatic equation of pressure variation, this term was not there. Otherwise, if I just remove this term, it becomes hydrostatic equation of pressure variation. P plus gamma Z is the piezometric pressure. So what's the difference here? In the hydrostatic pressure variation, the fluid was not in motion. Now the fluid is in motion. So when the fluid is in motion, so there will be some kinetic energy in the fluid as well. Only difference is that kinetic head has been added. Previously, there was hydrostatic pressure head. There was hydrostatic pressure. There was pressure due to elevation, but the fluid was not in motion, so kinetic energy was not there. Now the kinetic energy is also there. So this is the kinetic pressure. Okay, so rho V square upon 2, kinetic pressure. These are all in the terms of pressure. If you find the unit of P, it should be in Newton per meter square. Gamma Z should be in Newton per meter square. Rho V square upon 2 should be in Newton per meter square. They're all same units. I'm a homogeneous. The equation should be homogeneous. Each term should have the same units. Okay. And this thing is constant. Means now suppose if you have a flow where all these assumptions are valid. It is a steady flow, incompressible flow. You're talking about the longest streamline, and it is inviscid flow. Then between any 2 points in the fluid, you can apply Bernoulli equation. So at point 1, it will be P1 plus gamma Z1 plus rho V1 square upon 2. At point 2, it will be P2 plus gamma Z2 plus rho V2 square upon 2. And the summation of that is constant. So in a continuous motion of the fluid, at any point within the fluid flow, summation of these 3 terms will be equal. We are still following the same approach, that total energy remains conserved. So energy due to the pressure, hydrostatic pressure, energy due to the elevation, energy due to the kinetic energy, combine all that, the total energy should be same at any point. The energy is converting from one point to another, one form to another. Maybe some of the kinetic energy has been converted into hydrostatic pressure energy. Maybe some of the pressure energy has been converted into elevation energy. So they are interchanging, but their summation is same in any fluid. Okay. When we were talking about the hydrostatic pressure variation, there was no motion of the fluid itself. So rho v square upon 2 was already 0. Now there is a motion of the fluid as well, because itself now the fluid is moving. So we have rho v square upon 2 there added into the main equation. Do you understand these terms? Bernoulli's equation derivation is important, can come in the exam. Only those derivations which I tell you that, okay, these derivations can come in the exam, I can bring it. Because this provides a complete question where I have to first ask you to tell me what are the assumptions based on which the Bernoulli equation is based on. Then I can ask you to derive the Bernoulli equation. Then I can provide a numerical associated with the Bernoulli equation. So all things, conceptual, numerical, combined together, it's a complete package that can be given in the exam. And quiz 2. Not in the mid. Mid will be till fluid statics. Feeling the pressure already? This is just the beginning. Look, you have to follow through. If you go through it regularly with me, then you won't feel it. You won't feel trouble. Okay, but if you miss things in between, then you will feel a lot of trouble. Okay, so we have here terminologies here: P plus gamma Z plus half rho V square equals to constant along a streamline. Okay, this is in the pressure form. P plus gamma Z is a piezometric pressure. So basically Bernoulli equation says that the piezometric pressure plus kinetic pressure, summation of that is a constant, or summation of 3 things is a constant, which is hydrostatic pressure plus pressure due to elevation plus kinetic pressure. Summation of these 3 things equals to is constant. Okay, in the head form, okay, head form, like we previously made the equation in the head form, we can have the piezometric head P upon gamma plus Z. Piezometric head is a combination of hydrostatic head and elevation head. Okay, this plus velocity head. Now you have an additional velocity head, and this is also constant along the streamline. If you are writing the equation in the head form, all the terms should be in meter. P upon gamma meter, Z meter, V square upon 2G unit should be in meter. SI units. Okay. If you are writing in the pressure form, then all the units should be pressure. Okay. And should be homogeneous, uniform. Even within the pressure, you cannot say that, okay, you are writing P as in kilopascal and gamma Z is in megapascal. You cannot do like this. Okay, so it has to be homogeneous. Each term should be the same unit. Okay. The kinetic pressure is also called the dynamic pressure. The kinetic pressure is also known as the dynamic pressure. Okay, I don't know how, but I will look for it to somehow introduce this thing in exam. Okay, so that I just know that you know what is kinetic pressure and dynamic pressure. They both are same thing. I don't know how, but I will somehow find a way. Head, a term used to characterize the balance of work and energy in a fluid. Velocity head characterizes the kinetic energy of a fluid. Elevation head characterizes the gravitational potential energy of a fluid. Pressure head relates work done by pressure forces. Regular things. This is the Bernoulli's equation graphically represented in the flow in a Venturi. This is a Venturi. I think you have gone through with the fluid lab. You have seen the Venturi. Venturi is what? Yeah, we can measure the flow rate exactly through Venturi, but in generally Venturi is what? Venturi is basically you have a regular pipe, you put a restriction in a pipe and then you release it. So the flow will be first restricted and then return back. But by making this restriction, you can actually check that how the hydrostatic pressure is varying. And based on that pressure variation, you can actually determine what is the flow rate. So you made a restriction and then return back the flow. But by using that restriction, you can check the variation in the pressure, hydrostatic pressure, and you can actually, based on that variation in the pressure, you can judge, you can calculate that what would be the flow rate. So it's a device to measure the flow rate, Venturi meter. But in reality, it is just a restriction in a regular pipe. Okay. So suppose we have a Venturi which is installed in a tilted way, okay, and the fluid is flowing through the Venturi. Suppose we are assuming that it is an inviscid flow, it is a steady flow, it is incompressible, the fluid is a liquid, okay, and it is along the streamline. Obviously, it is flowing through the Venturi in a flow. Okay, what we are saying is that the total head is constant. This is Bernoulli's equation. So total head is composed of what? This will be the elevation head. Then if I attach a piezometer tube, then whatever the height of water goes into the piezometer, that will be the hydrostatic head. And then based upon the velocity, you will have the velocity head. Add these three heads at this point or anywhere in the flow, it would be same. So look here, from between point 1 to point 2, what is happening? The elevation is increasing. And since there is a restriction in the flow, because of the restriction in the flow, the velocity will increase. So the hydrostatic pressure head will decrease, such that the summation of these three terms would remain the same. Then if you further flow through the, go through the flow, if you come to the point 3, now the elevation head is increased further, but it will cause a decrease in the velocity head and the hydrostatic pressure head, so that the combination of these three still remains the same. So this is what Bernoulli's equations say. The combination of the three heads, if the flow is steady, incompressible, along the streamline, and inviscid. If these four conditions are met, that means at any point within the flow, the combination of these three heads would be same. If one head is changing, the other head will also change in order to compensate in a way that the summation remains same. Is it clear? Energy is conserved. Energy is conserved. This is what we are talking about. We are studying the fluid kinematics. We have not yet started to study fluid dynamics. नहीं यार, क्विज अभी मैंने बनाया ही नहीं. क्विज 10 मार्क्स का है ना. I'm thinking 3 marks conceptual देता हूँ, 7 marks numerical. But still मैंने अभी बनाया नहीं है. That's why बनाने के बाद डिस्कस करूँ तो ज़्यादा बेटर है. Okay, what I do is that quiz बनाने के बाद I will put it in the group. कि क्विज के अंदर डिस्ट्रीब्यूशन किस तरीके से रखी हुई है. ओके, बट इन जनरली न्यूमेरिकल कंसेप्चुअल दोनों ही होंगे. ठीक है, बट कंसेप्चुअल सिर्फ वही होगा जो मैं ऑलरेडी बता चुका हूँ कि दिस if there was any definition, I told that okay, you have to memorize that definition, then it will be there. If there is any derivation, then it will be there. If there is any anything, any concept which I said that, okay, this concept I can ask you in the exam conceptually, then I can say, but anything, whatever I have told, not beyond that, within the limits of what I have told. Okay, numerical be obviously from the lectures and from the homework. Okay. MCQs, MCQs, MCQs के साथ मेरा पढ़ा है. Okay, so let's. There is 15 minutes left. 14 minutes left. Okay, and look, the thing is that we have these two problems, and then this application of Bernoulli's, and then this spider tube. At least we should do till here. Okay, till here, please. Should I leave here? Okay, let's leave here today. Topic.